Welcome to the session. Today we talk about the mechanical unit operations, the subject. And this subject self-states that there is a mechanical unit operations and there is no chemical reactions. You may be surprised why the chemical engineers are interested in it, or why we have to study this, why this particular subject has kept in our GATE syllabus and all. See, basically this particular subject goes with the size reduction. How the size reduction can take place. So why the size reduction is required. So in our chemical industries, we don't deal with a very big coarse particles. We'll deal with the very small particles, because if you take the catalyst so the catalyst requires more surface area and if you take the packings, let us say, so the packings requires more surface area. Like that, we deal with the very small particles. We don't deal with the large particles. So our chemical reactions or separations, suppose if you take solid liquid extractions, in the solid liquid extractions also we make that the particular coarse particles or large particle, let us say large and small, we talk about the large particles called as, in this particular terminology it is called as coarse particles, right? So we make it at the ground to the level like powder type, amorphous type, so that the surface area, see, we are more interested in the reactions, or we are more interested in the mass transfer, more interested in heat transfer. So how that take place? Because of the surface. So how to do this? What is the efficiencies? How to reduce the size? This is what we have to do it. And also, once you take any crude and make it in that particular thing, suppose we have our material in it, we want to take it out. Like how to do it? Like aluminum is there, okay, gold is there, like that. Suppose if you are working in any metallurgical industries, because chemical engineers can work in more metallurgical industries in which they want to leach the copper, they want to leach the gold, they want to leach it. So by using the solvents or by different methodologies, they will be separating the components, and the required component is being extracted from that. So that is one example what we can take here. So most of the size reduction part will be talking about in it, and this particular subject is very simple, and it is being divided into two sections mainly. First half is divided into two sections. That is nothing but the classification and clarification. Two things we require here. So we classify the particles. That's what I am telling you, that if the crude is been given, how to separate our components. So classification, when we classify that particular particles by its density, by its size, by its surface area. So you take any parameter by which it has been classified, okay, thereby with that particular thing we can remove. So there is a very interesting method is there, like sink and float method. That is one type of classification. So what they do in this sink and float method is, they use this particular solvent, the density in between the two particles. Let us say there is a binary system. Okay, so two particles are there. So in that particular particles, what they do is they select such a solvent that its density is between these two. So the lighter particles will sink, heavy particles will float. The lighter particles will float, heavy particles will sink. So that is called a sink and float method. So like that. So colors are there. Then you can classify with the help of the colors, means like that. Clarification means complete removal, complete, like filtration is there. Filtration comes under the clarification, okay. And when cyclone separators also comes under clarification if very small particles are available, okay. But there's a large coarse particles are available, right? So that will come because we want to remove the solid particles from using the cyclone separators, like that. So clarifiers and classifiers, both I mean these are the two things what we are going to study in the first half of the mechanical unit operations. So what are the different types of classifiers are there? What are the different types of clarifiers are there? Okay. Then the next half we are going for the agitators. That is a different part of mechanical unit operations, because we have to design, because in the reactor we have to use the agitators. So what type of agitators are there? And in agitators what will be there? There will be blades will be rotating. So while the blades are rotating, what happens to our liquid? The liquid will be uniformly mixed, uniformly mixed, like, or uniform, you can talk about mixing, uniformly mixed, so that the reaction will take place faster. Even if you take in the crystallizer also, in the crystallizer we have to go for a very slow RPM one, so that what will happen is the sugar will not be concentrated on the one side, and the sugar crystals will not be formed. So uniform concentration, for that what we require is the agitators. So what type of agitators are there? Propellers are there, turbines are there. So impellers, we call it as an impellers. So how this impellers, design of impellers, what should be the standard turbine design, and what is the power number, and that is very important for us to calculate, so that we can design the motor, because the motor is required to run the turbines or run the impellers. Okay, so in that what we do is we calculate the power number. So that is very, very important, so that you can design a motor on that. See, in industry there are once you join any industry, first you should not concentrate on anything. So you have to concentrate on first what are the valves, different types of the valves. You have studied in fluid mechanics, and what type of agitators they are using in the reactor. Reactor is only a tank, right? Reactor is nothing but a tank. So nothing to, we can learn later. But first we have to, the end pumps. These three things, agitators, pumps and valves. These three things are very, very important. Even piping and all, design and all, we will be studying it. So what happens, you tell me, suppose if any problem is there with the pump, we cannot pump it, right? Once we cannot pump it, the things will be dried or the process will be stopped. Suppose the agitation is stopped. Suppose the agitation is stopped, what happens? So when there is a uniform agitation going on, what will happen is even the heat transfer will be faster, because if you send the coolant through it, what happens if you are agitating it? What happens is the heat will be taken out from this particular, because if it is an exothermic reaction, the heat will be taken out from that. Okay, suppose, and uniform concentration will be there, thereby the reaction rates also will be increasing, and the percentage conversion of the chemical reactant will be faster, and will be getting the products. Let us say, suppose the agitation has stopped and it is a highly reaction, heat transfer is not happening, then what will happen? There is a chance that there is an accident which can happen. Okay, so these three things first you have to concentrate, because we are all beginners, we don't know, only theory. That's what if I complete this one, second half we'll come to that and we'll complete that. So only theoretically we are completing. So practically what you have to do is, if you are in a final year now, you go to the industry and don't go for any process design and all, not required. First you go, first 15 days you concentrate on that, and the next 15 days you can go for the material balance or process calculations or the design of the reactors. So like that. Okay. So this particular subject goes with the two things. One is the classification, another is the clarification, and the third part goes for that. So in this particular classification, the size reduction, how we reduce the size. Okay. So now suppose the naphthalene ball is there. So naphthalene ball, you want to calculate how many days the naphthalene ball will come, or you can take the camphor, or you can take the Bombay Rava or Idli Rava, right? So how this particular otherwise Gemuka or wheat Rava, rice Rava. So how these people will make that particular particles. So even if the size is increased, you don't take it, right? So that for that they require some classification of that, because all this particular thing like sugar crystals are there. Sugar crystals, and if you go to different shops, different types of sizes will be available. Okay, so what are the sizes? Based upon that, you know Mishri, right? Mishri, because that will be given as a prasad in the temples. So that particular Mishri, how that will be beautiful crystal. If you put it in your mouth or if you put it in a water, it will dissolve completely. Whereas if you take some other things like raw mysteries and all, that won't dissolve properly because it is not properly being done as a crystal. So that particular particle, see, in this production, we'll be getting a different types of particles. The different types of particles we classify. And by classify with what? Classify by the size now, because we are interested in the size. So this is called sizing. Sizing means we use screens. Different types of screens we use. Thereby the sizes will be automatically being classified. Okay, like that we will be sending to the market, we will be packing it, and if it is a mystery, is very costly, right? Rather than if you go to any other shop, he says 20 rupees per kg is the sugar. In somebody if you go, then he says 30 rupees or 40 rupees per kg. Some shop you go, in a packet they will sell 60 rupees per kg. Then immediately you have to see here that why. Then if you ask him, he says, sir, you see the quality. So he sees the quality means what? It appears like a crystals. Okay, you know what is a crystal in the chemistry language. So like that. So it dissolves completely without having, it's a pure crystal like. Fine. So like that, the classification is very important in our, even if you manufacture the powders, like tablets, if you produce the tablets, if you, so even you have the gems, right? The people will be eating the gems. Nowadays you are seeing in the advertisement that different colors of gems are there. Okay, like that. So all the colors, that is the classification, that is the mixing can also be possible there, and the size will be the same. So like that, the different types of sizes will be there. Suppose if you think that all the sizes will be the same, no, there will be some wastage. What is the wastage? How the wastage is being removed from that? By classification. So by sieving, by sizing, these are the things will be done. Okay. So this particular subject is very, very important for us in the pharmaceutical industries, where we do the powder, right? We made, actually there are two things are there. One is called the bulk drugs and another is called the pharmaceuticals. So we have to be very clear that we work in bulk drugs. Bulk drugs means we'll prepare the raw materials for them. We take the raw materials, we prepare as a product, but this product will become a raw material for the pharmacists. Why? Because the pharmacist, suppose a crocin or a calpol, or if you want to prepare a paracetamol tablet, what do you have to do? That paracetamol tablet also you have to they'll take the powders, 1, 2, 3 powders, and they mix it and they press it, and they will be getting a tablet. Okay, in one company I was told, I don't want to take the name of the company, but I was told by one of the person who is working there, they have, as their pressing is not proper, hence they are not getting the round tablets. They have thrown the lakhs of rupees worth of tablets outside, because that is not up to the specifications. So like that, the size of the particle is very, very important for the selling. For our things, let us take the naphthalene ball. I'm just referring the naphthalene ball. If you purchase the naphthalene ball, okay, and how many days you expect that naphthalene ball to be there? At least we expect that 3 to 4 days the naphthalene ball has to come. If you take a camphor, if a camphor powder is available, camphor tablets is available. So if you take the tablet of the camphor, then if you just put it that particular camphor, you expect that the camphor will get. So because it is a sublimation, right? So the naphthalene or the camphor will directly convert into the vapor without converting into that, and you expect that. So how you calculate? How you calculate the mass transfer? How you calculate the rate? So by the size of the particle, by the surface area available, like that. Okay. So here in this particular, that's what these are the examples. Why should we study about the subject? Simply, as the syllabus is given, we should not read it. We should relate it, the particular subject, to our profession. Our profession is chemical engineering. So how the chemical engineering is there? How better I can utilize these particular subjects? Every subject is like a weapon for you. If you are good in using that weapon at the right time, at the right place, then you will shine like a chemical engineer. So without knowing it, you cannot. Suppose if the weapon is there, you don't know what is that. You cannot simply use it. Okay, like that. So you should know what is the things. Now coming to the, these are the first introduction for you, so that you can really understand the importance of the particular subject. Why should we study about it? And if you come to that particular particle, like if I say that naphthalene ball, for 3 days it has to come. So the calculation procedure is there. So how to calculate, how many days it will come. All the things, the calculation procedures will be there, but it all depends upon it. Then to calculate the surface area of a naphthalene ball, have you tried? Have you tried at any time what is the naphthalene ball shape? Okay, it will be round and it will be cylinder and it will be round there. So it is not possible for us to calculate. But what we assume? But we assume the particles, because once you size reduce it, it is not in your hands. But once you put it in a size reduction equipments, we don't have a control over it. It will give the product. The product will consist of different types of diameters. Okay, different types of diameters will size analyze with the, we sieve it, we analyze it, and then we will take out whatever the things we require. Based upon that, we calculate the efficiency of the reduction or size reduction equipments. Okay, so now then what you calculate there, how you calculate thing, then obviously we assume all the particles to be a spherical particles. Okay, so that is the main assumption what we take, unless until we can define that particular particle shape. So naphthalene ball shape will be completely different. It is not round. It will be in a different way. Okay. So we cannot define it. Even the tablet, what you get like a paracetamol, can you define what is that particular tablet? Is it a circular tablet? What is the surface area? How to calculate the surface area? Okay, like that. So what we generally prefer is to calculate the volume or calculate the surface area. We consider as a sphere, unless until it is a cylinder. If it is a cylinder, then we calculate the sphere. Suppose if you take the sphere, then we calculate with the sphericity. So some parameter has to there where we can relate that with the sphere. So relativity, everything is relativity. So we relate that particular thing with the volume or with the surface area or surface area to volume. Like that, we keep an ideal system called as a sphere. Then we compare that sphere with this and we calculate the sphericity of that. How much it is deviating from the sphere. Like if you have a cylinder, directly the sphericity of the cylinder will be given. Because the cylinder can be defined. Okay, cylinder can be defined. Even square can be defined. Rectangle can be defined. But uneven things which comes under the size reduction, Once you put a coal particles, let us say, you put a coal particles there. Then after that there will be some reduction. Then can you define that particular particles? We cannot define. If a mystery is there, you say it is a pure crystal, then you can find. What is the rate also you can find. Rate of dissolution you can find. The surface area you can find. Because it's all defined. If it is not defined, then we have to consider it as a sphere. And consider it as a sphere means not pure sphere. How much it is been deviating from that. How much it is, or not deviating, how much it is tending towards. More positively we talk about. Like how much it is tending towards the spherical. That is what we can think of. Okay, so why sphere only? The question is, why sphere? We can assume why the sphere is taken as the ideal thing. That is the main important aspect. Once you start mechanical unit operations, you have to start with the sphere. Because the sphere is the particle, ideal particle or base particle, you can call it as base particle. Then why this spherical particle is being used? Okay, so that is what we'll start with this. Now this is the background. Okay, now I think you know the seriousness of the particular subject. Generally what we think is the subject is very simple. We can read within 1 day or 2 days. Okay, but don't do that. But this is very, very important. See, all the subjects which are there, these are all, I told you that, these are all weapons. Okay, so you have to master in it all the weapons so that you can use it in your life. You take life as a war, then if you want to use a weapon, then how can you use the weapon without knowing it? Okay, so like that, if the life is a struggle, right? So we have to struggle day and day to prove ourselves or to be a successful person and be a more useful for the society, like that. So all these weapons you have to keep in a proper way, but without knowing it, you cannot just put it. Okay, like that. So with the known thing only, you have to use it. So why sphere? First question, mechanical unit operations, if you start, don't start with the size reduction. Okay, start with this particle size. Why sphere? Okay, so let us start now. Why sphere? So this particular, this is called as particle characterization. Please take the notes of that. This is very, very important. Particle characterization. This will be helpful for you in your future. So size of the particles. So what it defines is the particle of simplest shape. The particle of simplest shape is the sphere. That is what I am talking here about, is the sphere. In that because of its symmetry, the question of, this is very, very important, the question of orientation does not have to be considered. Why? Because if you see in all 3 dimensions, the sphere looks like the same. Okay, like in a snookers or billiards, okay, they use the spherical balls. So a player can rotate around that board, and with the then he can hit that particular ball, okay, at any direction and at any angle. Okay, like that. So you can see the wonders how the people will play for the snookers and all. If it is not a spherical one, if you take in a different way, then it is not possible. Even cricket ball is not a spherical ball. Okay, cricket what they play is not a spherical ball. But here, the snookers is a spherical ball because the orientation means the way you look. Like cylinder you take. Okay, cylinder orientation is what? If you see from the front view, it will be like a rectangle. If you see from the top view, it will be like a circle. So it is changing the orientation by changing the view. Whereas for the spherical particles, there is no orientation at all. So you can suppose, let us say, in a random packings, where we require interfacial area. You know what is interfacial area? That is the surface area provided by the packings, and on that the volume of the liquid spread. So it is meter square per meter cube is interfacial area, and per meter. The unit of that particular is per meter. Now how you calculate? Suppose if for the random packings it is falling like this. Suppose if it is falling like this, then the surface area you are going to calculate. Suppose it falls like this. So a different orientations will be there for if it is a cylinder. Okay, but in this sphere, whatever the orientation you take, there will not be any corners. Okay, there will not be any corners for the sphere. So if you see from the 10th dimension also, let us say, okay, if you imagine 3 dimensions, we can imagine 4th dimension, 5th dimension, the people will be calling nowadays. So if you see from the 10th dimension also, then it will look like a shape. So that is the main important aspect. Because of its symmetry, the question of orientation is very, very important to calculate the interfacial area or the surface area of the particular particle. Orientation does not have to be considered. That is the particle looks exactly the same. Whether from exactly the same from wherever direction it is viewed, okay, and behaves in the same manner. This is very, very important. Behaves in the same manner in a fluid irrespective of its orientation. No other particle has this characteristic. See, that is the advantage of a sphere. No other particle has this characteristics. Okay. So frequently, this is what I am talking about. This is why the spherical. What is spherical shape? What is a sphere? Now, frequently the size of the particle. Let us come to the subject now. The size of the particle. Now, whatever the size of the particle, we are going to get it from the size reduction of irregular shape. of irregular shape, because we don't have any control over that. Irregular shape is defined in terms of the size of an equivalent sphere. That's what I'm telling you. Equivalent sphere means we relate it to the sphere. Equivalent sphere. So how these are being classified? Some of the important size of equivalent spheres. Some of the important size of equivalent spheres are as follows. Means whatever you want here, you can relate it to your irregular shaped one. First one, the sphere of the same volume, as the particle. Means we are relating with the volume. Means whatever the irregular shape has come, we take it as a volume of the particle. The sphere of the same volume of the particle. The sphere of the same surface area as the particle. Same surface area of the particle. And third one is the sphere of the same surface area per unit volume of particle. Say, per unit volume of particle. So they are referring with surface area and volume of the particle. See how many things that we can assume our irregular shape of the particles. So the sphere which will just pass through the size of the sphere, through the size of square aperture as the particle. This is very interesting. We'll discuss on this. As on screen. And the fifth one, last one, the sphere. See, there is another important one. Sphere with the same settling velocity. With the same settling velocity as the particle. Velocity of the particle. See, this is what I have forgotten to explain to you. It is the sphere, how you calculate the settling of that particular particles. So we assume it as a sphere. Galena particle if you take, then we assume it as a sphere. Whether it is a sphere, it is not a sphere, but we assume it as a sphere as the settling velocity of we call it as a terminal velocity. By the terminal velocities also, that is one type of classification. Okay, we have talked about the size, we have talked about the color, we have talked about other things, but the settling of the particles, like I have mentioned that sink and float method. Okay, like that. If the sink and float method, if you take, then the solvent only we are using, that particular solvent density will be between the particles. So some particles, lighter particles will float, another particles sink. Sink means they are dropping down. Dropping down means with certain velocity. So what is that settling velocity of the particular thing? This will be helpful for you where can you tell me where this particular what is an application of this particular settling velocities? The settling velocities, thickness. You know what are thickness? The thickness are clarifiers. Thickness are clarifiers. Means suppose if you want you have a solid particles which are coming it out. Suppose water purification you take. In the water purification and all, we use a thickness like a agitator will be there. Very slow agitator will be moving, and the particles which are coming it out, they will be removed. Okay, so same settling velocities will provide the settling velocity. So thickness design, in the thickness design, this will be very, very helpful for us. Okay, so you can write it like design of thickness. This will be helpful for us as a chemical engineer. Design of thickness, because we should know where exactly. So thickness design will be there in the academic one. Please don't miss that. You have to calculate it, but not in their GATE syllabus. But you can know what is the thickness, because if you want to remove the large number of the particles, we are not classifying, we are clarifying. Means we have to remove all the particles, like small particles or big part, we have to remove it. So that is called as a thickness. Thickness means they concentrate the solids at the bottom. So by their rotation, the design is there. So if you can talk about the thickness there, so it will be used. Now this is the fourth one, the sphere which will just pass through the size of the square aperture. So what happens, I told you that if you take a sugar industry, I told you, the sugar crystals will not be uniform. It will be different size of the shapes. But I told you that we use the screens, we size it. Screen means what? A screen means it is a woven material. Like they take one metal sheet and then they will weave it with the some iron threads, okay, or steel threads or plastic threads, different types of material they can use it, so that it will not be reacting with the other material and all. So inert materials they will be taking and they will be weaving that particular thing. Weaving means the size of that particular aperture. We call it as an aperture. Aperture means once we weave anything, what will happen is we keep that a small hole like, okay, a small hole like, thereby we weave it in such a way that there will be small holes like. That's why we call it as a screen. So what we do is we take that particular, we weave it, and then that particular size is being defined, and based upon the size of that, the screen number is being defined. So this particular sphere will just pass through the size of the square aperture. Means if we want to know the critical radius of that particular critical radius means exactly that particular particle will stick into that. You might have observed in your lab once you are doing the mechanical unit operations, there will be some particles will be exactly fitting into that. Okay, that particular particle, that is what it is being done. The sphere which will just pass through the size of the square aperture of the as the particle. So that is the speciality of the sphere. So once you start the mechanical unit operations, first you have to consider about the sphere. Now, and I told you that what is a parameter? How much it is tending towards the sphere. That is what very, very important. And for that, I told you that a parameter called sphericity is being used. So a measure of particle shape. A measure of particle shape which is frequently used, is the sphericity phi. Is the sphericity phi is defined as phi s is defined as phi s is equal to surface area of sphere, surface area of sphere of same volume of particle, volume as particle, divided by surface of the particle, surface of the particle. So if it is a sphere, phi s will be 1. So asperity is given as so this is the definition of the sphericity. Okay, so here the definition of sphericity is phi s. So this is the sphere quality here, how this it is been calculated, right? Now once we talk about the sieves here, the particle size is over. Now what we have to talk about? We have to talk about the screens now. What type of screens you have to use it and how that is being defined. And what are the standard screens which are available in the market, and that we have to know. So sieve analysis. Sieve analysis. Sieve analysis sieve analysis may be carried out using a nest of sieves. Each lower sieve being of small aperture size. Small aperture size means we keep the larger screens, larger diameter screens, means the aperture size will be greater. Okay, and then as it is coming down, we'll keep the larger diameters, then the relative thing will go on decreasing the size. So sieve analysis may be carried out by using a nest of sieves, means not only one sieve, we will be having a nest of sieves, each lower sieve being a small aperture size. Generally a sieve series are arranged so that the ratio of aperture sizes on consecutive screens is 2, 2.5, 2 to the power 1/4 according to the closeness of sizing which is required. Okay, then the sizing, I will write here, the sizing the sizing is based purely on the linear dimensions. Is very, very important. On the linear dimensions. See, we don't know from where the questions will be asked. Okay, so concentrate on this particular points. The size is based purely on the linear dimensions of the particles. The question may be asked like, the sizing will depend on non-linear dimensions, linear dimensions, square dimensions, or some other dimensions. Okay, like that he may ask for the 1 mark. Because in the gate, because you know, now you are experienced with the gate and all. Okay, you know that the gate problems won't come from the test work. Right, it is not like, it comes from the concepts, it comes from the theory. So theory is very, very important. So whatever I am giving it, please take it, write it in the notes, okay? And then each and every point you kindly analyze, because any question may be asked from these things. So the sizing is based purely on the linear dimensions of the particle, and the lower limit of size which can be used is determined by two factors. A, the first is that the proportion of free space on the screen surface becomes very small as the size of the aperture is reduced. So this is very, very important thing. The first is that the portion of free space on the screen surface becomes very small as the size of the aperture is reduced. B. The second is that attractive forces between the particles is very, very important. We'll discuss about this. The second is that the attractive forces between the particles becomes larger at small particle sizes. And consequently the particles, this is very important now, the particles tend to stick together and block the screens. So this is very, very important. Sieves are available. Sieves are available in a number of standard screens. Okay, this is the very important one. Let us go through once again. The size is based purely on linear dimensions of the particles, and the lower limit of the size which can be used is determined by two factors. One is, the first is that the proportion of the free space on the screen surface becomes very small as the size of the aperture is reduced. So, if the size of the aperture is reduced, what will happen? The free space will become very less. Because why? Because the particles will not able to leave the screen. Okay, they cannot go from the screen. So that is the first point. The second point is why they are not able to go. Why there is no free space means what happens is, if you take the small particles, what will happen? See, as that is the problem with the nanomaterials. So nanomaterials, the people are talking about nanomaterials, nano and all. But it is very difficult to handle the nanomaterials. Why? Because these nanomaterials are nano means 10 to the power minus 9, right? So that much of small particles are there. If you go on grounding the particles, then what will happen? The intermolecular attraction forces will be very high. So if you keep together, they will agglomerate. Technically we call it as a agglomerate. Agglomerate means they will attract each other and then they form a big particle. Like how this hills have formed, rocks are there. How that has formed? Because of this particle sizes, very small particle, maybe 1,000 years or 1 lakh years or something else. How these hills are there? This is nothing but the agglomeration of all small particles get together naturally, then they are forming a very big structure like. Okay, so if small particles you take and if you go on with the very small size of the aperture, then what will happen is, if the free space is not available, and if I told you that because the aperture size is very small, you can understand that all the particles will remain. No particle can underflow or no particle can pass through the screen. So what happens is, if the time is been given for the particles will stick on each other and agglomerate or increase the size, thereby blocking the screens. So these attractive forces tend to stick together and block the screens. The screen, right, this is the main important aspect of the sizing. So this is the very important part here. Okay, the question may be asked in it. So in the gate, we should be very smart enough for preparing the subject, not like an academic one. In academic one, you don't study all these things. Why? Because it is not required. Directly, your professor will start directly with the screens or directly with the size reduction equipments. So that is not the thing. For the gate, we should go with the roots. We should know what is the thing. There is only the asked, okay? They don't ask very big questions. Like in academics, you have half an hour to solve. But here, you have only, you know that, okay? You have only 3 minutes time. So you have to solve within 3 minutes. So the question has to be prepared. The question has to be prepared in that way. How can the question can be prepared? The question can be prepared from these concepts only. Okay? So like that. Please follow it, okay? Whatever I am teaching here, kindly follow it. It will be highly useful for you to increase your knowledge also. Okay? Tomorrow you may work in the industry and these particular points will be definitely helpful for you. Okay? So, this is the a general introduction about this one and sieve analysis. We take a small 5 minutes break and we'll come back.